right, so in this section of the course, we're going to talk about asynchronous programming, and specifically, we're going to focus on the async and await keywords, because strictly speaking, everything that we've been doing up to now is asynchronous programming, because when you spawn threads, you're doing things out of sync, and so it's all asynchronous programming, but we're going to focus on the async and await programming model, something that people also call coroutines, although that word isn't much used in C#. It is used in other programming languages such as C++ or Kotlin, for example. So that's what we're going to talk about. So what is the problem exactly? Well, if you think about typical .NET calls, they're typically blocking. If you call a function foo, for example, that blocks the entire thread up until the point when foo is actually finished. So here I have int n equals foo, so you only get the value n when foo is done executing, and that's when you can call bar. Now, there is a big problem with this if you take this code and you, for example, call it on a UI thread, and the problem is that you're blocking the UI thread, essentially. So the question is, why should foo block the current thread, the thread that you're currently in? Because essentially, what you can do instead is you can run foo and indeed bar in a separate process without blocking the UI, for example. So why can't we take foo and run it in a separate thread? Well, we can. We can actually take foo and just explicitly spawn the thread. But then what we want to do is we want to have the function bar, the method bar, to use the result of foo. So in this case, foo would run on a separate thread and bar can be a continuation of that thread. So of course you can do this manually. I mean, you can just spawn a new thread and you do foo in that thread. So in this case, we have threadpool.queueUserWorkItem, or if you want to use the fancy new TPL task pool, that would be task.factory.startNew, something to that effect. And then, of course, you can take bar and you can say, well, we're going to have a task doing foo, and bar is going to be part of the continue with call. So it's a continuation of that whole thing. Now, you can do that. Right now, today, there is no problem doing it. You could have done it for quite a long time because we've had threading mechanisms since the very early versions of .NET Framework, but it's not particularly convenient. It's a bit too cumbersome. Specifically, what we want to do is we want to keep writing code as we've been writing code, one statement after another. We want to use the ordinary programming model of statements coming after statements. We don't want to juggle lambdas or create separate objects or any of that stuff. And in addition, we also want the flexibility. We want the flexibility to take these methods, foo and bar, and we want to either call them synchronously on the current thread, thereby blocking the thread, or asynchronously. So we want to be able to have this choice without without having to switch from, let's say, some external structure and writing it one line after another. Now, this idea of being able to resume something, it's actually already in the .NET Framework, because we already have a resumable paradigm, and this is coming to the history of where the async and await keywords come from, because we have the yield keyword, and the yield keyword is very interesting in .NET because it allows this sort of temporary suspension of execution, and that's when, you know, you're iterating some container, for example, and it keeps yielding you values, but you can pause at any time, you can do your own work, and then you can come back to getting the next element from the container and getting that. So that is how the whole async await story started, because essentially what happened is a guy by the name of Jeffrey Richter, he created this library called power threading, and it had a type called async enumerator. And the idea behind the async enumerator was precisely this. It was this idea that you can have things happening on separate threads, and it was actually leveraging the yield keyword to suspend the execution until you have the next piece of the puzzle, so to speak. Now, the .NET Framework's async and await keywords, they kind of make the whole thing official, basically. So they give you a programming model where you can, instead of actually, blocking the current thread, you release the current thread immediately. You start doing things on a new thread, and you have these continuations one after another. Now, of course, in order to understand all of this, we have to understand how the async and await keywords actually work, because their implementation is not intuitive. The way that they are done, it's not easy to understand. But let's jump into it anyway, and we're going to talk about how it's all done. So we have this async keyword, and this actually changes the way that you write your methods if you want them to comply to this new programming model. So if you have a method, let's say you have a method which is called calculate, it returns an integer, for example. What you would do is you would change this method to make it asynchronous, to make it compliant with this asynchronous model, and you would change it in a very strange way. So you would maybe add the word async to the end of it just to indicate it is asynchronous, and instead of returning an int like we do in the previous example, you would return a task of int. Okay, so what does this give you exactly? Well, task of int kind of hints to whoever's actually consuming it that you're making a task, and that task can be executed on a separate thread in the TPL task pool, and therefore it can be part of this whole asynchronous game, so to speak. So we don't have the async keyword here just yet. We'll meet it in just a moment, but the interesting thing about this part is that internally, if you look at the contents of calculate and calculate async, they are identical methods. They can have identical bodies. So both calculate and calculate async, they can, for example, return the value 123. And it's interesting because in the second example, in calculate async, you're returning a task of int. So you would expect somebody to actually manufacture a task and return that, but you don't have to. You can just return an ordinary value. And the interesting thing about this part is now that you've transitioned from defining your method as just an int returning to a task of int returning, what you can do is you can now consume it as follows. So this is where the async keyword actually comes in. So you have a method called foo, and it can now await the result of calculate async, and as a result it has to be decorated with the async keyword itself. So here we see both await and async, but we see them in a really kind of bizarre and strange way, and it's still not clear. It might not still be clear to you how exactly does async work. So let's try to answer this question. What does async actually do? Well, the answer is not much. In actual fact, the async keyword does not in any way change the code that's generated by the compiler. So you can think of it as a kind of hint to the compiler, and all this hint does, there's only one thing that it does, it enables the use of the await keyword. And this might seem particularly crazy. I mean, why do we have to have two keywords if you could just have the await keyword? So the async keyword informs the compiler that whenever it sees the await keyword, it's actually a special keyword, not just an identifier for a variable. Now you're probably wondering, why on earth is this necessary? And the reason why it's necessary is because await wasn't a reserved word since the beginning of C#, which introduces its own problem in that you could end up with ambiguities. If somebody declared a variable to be called await, for example, you still want that part of code to work somehow. So this is what C# did. It essentially introduced two keywords where only one keyword is required. And if you look at other programming languages, let's take C++, for example, they actually call the await keyword, they call it co_await, just to mitigate this problem. Now, C# didn't go that route. It introduced an extra keyword in this case. So essentially, the async keyword, it kind of changes the semantics of the await keyword, but by itself, it doesn't do anything. So we're mostly interested in the await keyword because that's actually the thing that does quite a bit of work. So what does await do? Well, first of all, you have to realize that the await keyword does not perform a physical wait. So a typical wait is when you call something and you wait on the result, like a thread, for example. So calling, for example, await calculate async is not the same as calling calculate async, which gives you a task, and then waiting on that task result. That's absolutely not what it does. And you should not think of await as any kind of, let's just wait for this to complete. That's not how it works, because if you calculate async and then wait for the result, you're actually blocking the caller. So if you're on the UI thread, for example, you're blocking the UI thread, which is absolutely not what you want to do. You want to avoid precisely this situation. An interesting thing to note is there is no explicit unwrapping here. So await, even though it gives you a task of t, it actually coerces that value from the task. So you can say int foo equals await calculate async, even though calculate async actually returns a task. So await kind of forces, it gives you the value of the task result. Now, another interesting thing is that you complete the continuation in the same synchronization context where you started. So if you started on the UI thread, you can perform your work on a separate thread. That's when you await the whole thing. But subsequently, when you take that value and you use it to update a control, for example, you're back to the UI thread. So here is a very kind of simplified, very silly illustration of what await actually turns into. So let's suppose you write something like the following. You have you're awaiting. So you await calculate async, you get that value n, and then use that value to update a control on the UI thread. Obviously, that has to happen on a UI thread. So what you really end up with is something which is more or less like the following. So if you imagine calculate async as a task, just an ordinary TPL task, then what happens is the following. So you first of all take calculate async and you start the task. So you let the task complete, but you let it complete on a separate thread. And you're probably wondering, well, hold on, if it's completing on a separate thread, what's happening to the current thread? And the current thread is, well, effectively, you release the current thread. You're no longer using it. So you calculate async on a separate task in the TPL task pool, and then you define a continuation where the result of that calculation, the result of calculate async, is actually taken out from that thread and is being used to update the text box in this case. But the interesting thing is that this continuation happens on the synchronization context that is related to the location where you started. So that's where, you take synchronization context, the current, you look at it and you say, well, if it's not null, then let's just update on whatever thread we were on. So if you fire this whole thing from a UI thread, you're guaranteed that the continuation is actually going to work correctly, because if you imagine this continue without the synchronization, it's just going to throw an exception. It's going to say, well, you can't update the UI thread from a different thread. That's not how it works. You have to either use the dispatcher or whatever. You have to check for invoke required, and you have to do invoke. So that's an additional benefit here. So let's kind of recap what the await keyword actually does. So first of all, it registers the continuation with the async operation. So in other words, when the compiler sees the await keywords, it knows that the code which follows the await keyword is a continuation. Kind of like when we do continue with. Everything that comes after the await has to be a continuation of whatever await is actually waiting for. Now, what await does then is it gives up the current thread. So the current thread is released. It's basically, it's over. We no longer do anything on the current thread, because even though the code looks like it's a synchronous code, the await keyword makes sure that everything after it happens elsewhere, happens on the TPL thread pool. So the call is where the call to whatever we are awaiting is happening on a thread from the TPL thread pool. And then, of course, we check the synchronization context. So if the synchronization context is not equal to null, then we make sure that the continuation is actually posted there. So if you're on the UI thread, we'll make sure that the whole thing actually gets posted on the UI thread. However, if the synchronization context is in fact null, then the continuation is scheduled using the current task scheduler. Now, you can customize this behavior, by the way. You can, when you await foo, for example, you can say await foo dot, and then you can customize this behavior by, for example, preventing the use of the original synchronization context. And finally, when you get the result of the await, that result is coerced into the actual value. So if you get a task of int as the return type, the signature to an asynchronous method, you get that int, and you can say int n equals whatever. So that's how the await keyword works. And now we're going to take a look at the actual code. We're going to see what the code looks like when you work with these concepts.